Right now, governments and tech companies are spending billions trying to figure out how to pull heavy freight without burning fossil fuels. The sheer size and momentum of modern supply chains make battery-powered long-haul trucking a massive engineering headache. But a fully operational, emission-free heavy logistics network already existed. It was running in Sweden 8 decades ago. To understand how they achieved it, we have to look back at a moment when the fuel simply ran out. In the fall of 1940, global supply lines collapsed. World War II blockades abruptly severed Sweden's access to imported gasoline and diesel, bringing the country's transport network to a sudden standstill. This created an immediate threat to the food supply. The Tre Kronor mill, situated on the island of Kvarnholmen, processed the flour, bread, and pasta that kept the population of Stockholm fed. Without fuel, those supplies were trapped on the island. Out of desperation, the nation pivoted to an emergency fuel called gengas, or wood gas. They attached bulky combustion generators to the backs of vehicles, burning chopped wood or charcoal to capture the combustible fumes. These systems were incredibly cumbersome. A wood gas generator took up to half an hour just to warm up, produced a fraction of the horsepower of liquid fuel, and leaked highly toxic carbon monoxide. Hauling tons of grain and bread from the Kvarnholmen docks up the steep hills into Stockholm required immense, consistent power. The wood gas engines simply choked under the weight. A heavy industrial supply chain falls apart if it relies on compromised, low-power substitutes. To keep the city from starving, the mill needed a power source that wouldn't fail on a gradient. The company running the mill, Cooperativa Förbundet, looked to the one abundant domestic energy source they had left, Sweden's national hydroelectric grid. Instead of trying to patch the combustion engine, they tapped directly into the power lines overhead, adapting urban passenger trolleybus technology for heavy industrial freight. Because of severe wartime rationing, raw materials like steel were heavily restricted. They couldn't manufacture new electric trucks from scratch, so they improvised. Engineers took standard ACEA electric passenger buses, ripped out the passenger cabins, and heavily reinforced the underlying chassis so they could pull massive cargo trailers. These converted machines were no longer transit buses. They became industrial workhorses, capable of moving tons of food through the city without a drop of oil. The new electric fleet immediately faced a severe physical test. They had to drag trailers loaded with up to 8 tons of cargo from sea level straight up the steep inclines of the Henriksdal Hills. This diagram shows the specific physics working against the truck. To move the payload, the vehicle must overcome a specific drag force, a combination of the sheer mass of the trailers, the friction of the tires, and the angle of the hill pushing the weight backward. A standard combustion engine struggles here. It has to rev up to a high RPM and shift down through gears to build enough mechanical power to pull. An electric motor works differently. Operating on 700 volts of direct current, these electric motors delivered maximum linear torque the millisecond the driver pressed the pedal. This allowed them to pull massive stationary loads smoothly from a dead stop on the steepest parts of the route. The inherent physics of an electric motor make it uniquely suited for moving heavy, dead weight through a hilly urban environment. With the physics solved, the electric trucks ran a continuous, emission-free loop. They loaded up at the Kvarnholmen docks, crossed the Danvik Bridge, and drove straight into the dense neighborhoods of Södermalm. To maximize efficiency, engineers built a dedicated offloading ramp directly into the middle of Folkungagatan, a major city street. The trucks drove straight down this ramp into Södra Station, transferring the flour directly onto the national railway network. The system succeeded because the city adapted its physical infrastructure to support the vehicles, fully integrating the clean supply line into the urban layout. Yet, in the autumn of 1959, after nearly 20 years of daily operation, the entire electric truck fleet was decommissioned, and the overhead wires were pulled down. The post-war economic boom flooded the global market with cheap oil. Suddenly, diesel engines were inexpensive to buy and very cheap to run. At the same time, Stockholm was undergoing massive roadway expansions. City planners viewed the network of overhead trolley wires as an inflexible constraint that cluttered the skyline and complicated construction. Faced with the convenience of cheap oil and the desire for unconstrained mobility, the city dismantled a functional, zero-emission technology. Today, almost no trace of this network remains. The only physical evidence left on Cornholmen are the heavy concrete bridge abutments, standing silently near the water. Those decaying pillars stand in sharp contrast to the billions of dollars currently being spent to rediscover clean trucking solutions. The Cornholmen experiment demonstrated that emission-free urban logistics could be scaled and sustained using existing mechanical principles. When absolute necessity demands it, radical, sustainable infrastructure shifts are entirely possible because we have already done it before.